series of electric circuit analysis. So we were looking into the transient analysis of electric circuits, and in the previous lectures we have seen how the circuit elements, resistance, inductance and capacitance behave under transient conditions. Okay, so resistance is a non-energy storing element, so it doesn't store any energy, so therefore the initial conditions in resistance are absent. It is a linear element, whereas inductor, under transient condition we have seen it behaves open circuit, okay, if no initial current is present, and under steady state condition it behaves as short circuit. If there is any initial condition present, then the initial current, with some initial current, the inductor behaves as a current source under transient condition, and it behaves as a current source across short circuit under steady state condition. On the contrary, capacitor behaves complementary to the inductor. Under steady state condition, capacitor behaves as open circuit, and under transient condition, capacitor behaves as short circuit. If there is some initial voltage present, then capacitor behaves as voltage source under transient, and it behaves as voltage source in series with open circuit under steady state condition. So with this knowledge of capacitor and inductor, we shall now move ahead to find the transient response of the various circuits that we will be studying in the forthcoming lectures. Okay, so first we will look into the transient response of a series RL circuit with the DC excitation. So whatever the analysis we are doing initially, we will start with the DC excitation, then we will move ahead with the AC excitations. Okay, so a circuit are of two types under consideration for transient analysis. Okay, it can be a driven circuit and it can be an undriven circuit. A driven circuit means the circuit with source. A circuit with source, whether it is a current source or voltage source, some active source or some active element is present in the system or in the circuit, such a circuit is known as driven circuit. Whereas undriven circuit is a source free circuit. Source free circuit. So this circuit comes with no source. Okay? So these two types of circuits are there under consideration. So we shall analyze both the circuits which are connected with series resistance and inductance, and we shall see how the current and voltages are behaving in the circuit. So first we will look into the transient analysis of driven circuit. First we will take driven circuit. Let us consider first a driven circuit. So this circuit comes with a source of V volts connected to a switch. I have a resistor R and inductor L of self-inductance. The voltage across R is VR of T. This is the self-inductance of the inductor. Let this be VL of T. Is the voltage across inductance. And this switch will be closing at T equals to 0 instant. This always this already we have assumed that the moment when I operate the switch from its previous state, in the sense I can operate switch from open condition to closed condition, or from closed condition to open condition, or from one state to the other state. In forthcoming circuits we will see. So the time instant at which I am operating the switch, or the time instant, we call it as the transition. So when the transition occurs, it occurs always at time instant t equal to 0, and this circuit carries a current, say I of t. So I am taking all the voltages and currents as function of time, because I want to know with respect to time how these are behaving. Let us assume, let this be switch K, I will give the name K. Okay. Assume that switch operates at t equals to 0. Operates at t equals to 0. Okay, this is one assumption. Second assumption is, before a transition in the sense operating the switch, before the switch is operated or before transition, switch is open for a very long time. Switch is open for very long time. The second assumption will give us the clarity that if there were any transients happened earlier, when previously the switch was operated, those transients have already died up, have decayed, so that there are no more effect of previous transitions are retained in the circuit. Okay. So with this assumption I start my analysis. Now what I am analyzing in the sense, I want to find out what is the value of current I of t. It means the expression for the current I of t. So to know the value of current I of t, and we know that there are some initial conditions will be present in the inductor, because inductor is an energy storage device. So there are initial conditions possible. So to know what initial conditions it contains, I should be first knowing what are the initial currents in the circuit. Okay. So to know the final expression of the current, I should be knowing initial condition of the current. Now observe this assumption that before transition has occurred, or before the switch is operated, or before the closing of the switch at instant t equal to 0, the switch is open for a very long time. So it means that the circuit is under open circuit. Okay. So for t less than 0, switch K is open, and I of t, the current in the circuit is 0, because it is an open circuit. So therefore I can say, therefore the initial condition I of 0 minus is denoted as I naught, which is I of 0 minus, which is I naught, is 0. So the initial condition in the circuit, the current circuit under consideration, is 0. So there is no initial condition existing. Now for t greater than or equal to 0 plus, the switch is closed. T greater than or equal to 0 plus. And this is also equals to I of 0 plus, because we know the current in inductor doesn't change instantaneously. So that is equals to I of 0 plus. Let us not worry about that as of now. We will see what happens later. Okay. Let me take only I of 0 minus as 0. Now for t greater than or equal to 0 plus, switch is closed. So the circuit will be, this is switch K, this is resistance R, this is VR of t, this is L, VL of. Now I need to find what is the current I of t. What is the current I of t? Now I need to find this. So to get that, apply KVL to the loop. Okay. So with KVL to the loop, what I get? It is V minus I of t into R minus VL of t, or in the first place I will take it as minus VR of t minus VL of t equals to 0. So there are three elements, there are three terms. I will rewrite this as VR of t minus VL of t equal to V. Sorry, I will rearrange the terms. VR of t plus VL of t plus equals to V. So what is VR of t? I get I of t into R plus VL of t is L di of t by dt, which is equals to V. Now let me take this as equation 1. So this equation 1 is a non-homogeneous equation, because there is a RHS non-zero term. Okay. So I will rearrange the terms here. I take I of t plus L over R di of t by dt equals to V by R. Okay. So earlier in equation 1, each term was representing the voltage In this expression, each term is representing current. I of t is a current. L di by dt is a voltage across inductor divided by resistance is the current. Voltage by resistance is the current. So the same equation is now represented in the form of a current equation. I of t minus V by R di of t by dt. Right, this as L by R di of t by dt equals to V by R minus I of t. V by R minus I of t. Okay. Or I will write this as di of t divided by V by R minus I of t equals to this L by R will go as R by L into dt. Okay. So this is one form I have reached. Let me take this as equation 2. Let me take this as equation 2. Now, to find I by I of t, I will be integrating equation 2 on both sides. Okay. Now, on integrating equation 2, on both sides, so it is 1 by the function, it will be natural log of V by R, minus, because it comes with minus sign here, minus natural log of V by R minus I of t equals to R over L into t plus some arbitrary constant k dash. Some arbitrary constant k dash. Now this is the solution. Let me take this as equation 3. Some equation 3. Now to find the actual value of I of t, I should be knowing what is the arbitrary constant k dash. Now k dash can be known from the initial condition of the circuit. Okay. So here I can write k dash known from initial condition. K dash can be known from initial condition. Now what initial condition we have assumed? Okay, we have I of 0 minus is equals to 0. So what does it mean? That is at t equals to 0, I of t is 0. Now if I substitute the value of t equal to 0 in this above expression, okay, then I will be getting the expression for k naught, k dash. Then I will be getting the expression for k dash. For t is equals to 0, so I can write minus log of v by r minus I of 0 equals to r by l into 0 plus, okay. So this implies here minus log of v by r minus 0 equals to k dash. Therefore I can write k dash equals to minus log of v by r. K dash equals to minus log of v by r. So let me take this as equation, say what number was the last? Equation 4. Now substituting the value of k dash in equation 3. So substituting value of k dash equal to minus log v by r in equation 3. Substitute k dash in equation 3. So what we get there is minus log of v by r minus I of t equals to r by l into t plus, sorry, not plus, minus log of v by r. Minus log of v by r. Or I will rewrite this log of v by r minus I of t minus log of v by r equals to minus r by l into t. Minus r by l into t. So we have log a minus log b as log a over b. So I will use that property of logarithm. Okay. So I can write log of v by r minus I of t over v by r equals to minus r by l into t. Now if I want to take out the logarithm, then I should be applying anti-log. Okay, so now take anti-logarithm. So what we get here is v by r minus I of t divided by v by r equals to, so when I take anti-log of this RHS, it will become exponential. So e to the power minus r by l into t. So rearranging the terms, okay, or I will rewrite this as v by r minus I of t equals to v by r e to the power minus r by l into t, or the final expression for the current I of t is equals to, I can write v by r, okay, minus v by r e to the power minus r over l into t. So this is the solution. So let me take this as equation 5. So this is the solution for the non-homogeneous equation that we have defined at in equation 1. Okay. So when we have seen the non-homogeneous solution, solution of non-homogeneous equation initially, there we had two parts of the solution. One was particular integral and one was complementary function. So particular integral was representing the steady state response, and the complementary function was representing the transient response. So here there are two parts of the solution or the response, okay, that the first term indicates the steady state response, okay, which is due to the voltage source applied to the circuit, okay, and the second term represent the transient response or the natural response, which is not due to the voltage source. It is because of the nature of the system. The second function is because of the nature of the circuit, whereas the first function is solely because of the applied voltage or the source connected to the circuit. So here V by R, okay, it is the steady state response. V by R is the steady state response, okay, due to voltage source, whereas minus V by R e to the power minus r over l into t is known as transient or natural response. Okay, and it is not due to the voltage source. It is due to the nature of the circuit and is not due to the source connected. Okay, so this is the solution. Okay, this is also known, if this is natural response, then steady state response is also known as forced response. Okay. This is also known as, the steady state response is also known as forced response, because this response is due to voltage source, which is the forcing function of the circuit. Okay, so the response which is due to forcing function, okay, is known as forced response. But one thing is clear from the expression 5, equation 5, expression of the total solution of the circuit, of the system, is that the variation of current is exponential with respect to time, because there is an exponential term present. But when I consider the initial condition of the circuit, which is 0, at t equal to 0, the current is 0. Okay, so therefore I can say from this expression that in an RL series circuit, the current rises exponentially with respect to time. The current rises exponentially with respect to time until the steady state is reached, and once the steady state is reached, then the current will remain of the steady value. So what is the steady value of the current? It is V by R. The steady state value of the current in RL circuit is V by R. Now whereas this transient, the transient condition will not exist forever in the circuit, it will exist only for the certain period of time, okay, or certain time instants, okay, depending upon the value of R and L. See, the exponent is having a power R by L. So the value of this exponent is depending upon the value of R and L. So depending upon the value of R and L, this exponential term or exponential nature of the current will exist, and after some time that doesn't exist. What is that, and for what amount of time it will exist, and for what amount of time it will not exist, we shall see again.